I'm William Bowen. I'm a field applications specialist at Purolite, and this webinar is about process intensification strategies to improve Protein A resin cost effectiveness. So I'll be covering the principles and benefits of process intensification for downstream processing. I'll cover the cost effectiveness in Protein A capture steps. I'll provide an overview of various scenarios, optimizing towards cost effectiveness. And I'll talk about reductions in buffer consumption using Purolite's jetted beads. So Purolite forms part of Ecolab's family of brands, sharing the common goal of protecting resources vital to life. It stands to benefit from Ecolab's appetite to invest and innovate in Purolite's future, as well as reinforcing our supply chains, security of supply, and overall technical expertise. This means greater coverage and experience for our customers around the world. So process intensification originates in the chemicals and petrochemicals industries. It's intended to increase the efficiency of an existing process by improving upon prior design inefficiencies. So you're essentially getting more for less or more per unit equipment size. This means you'll see reductions in material consumption and waste generation, reductions in processing time, energy consumption, as well as reductions in manufacturing costs and lower footprints. So again, the emphasis is on more for less. So this can manifest in a range of ways, from single-use items to pre-packed chromatography columns, as well as more advanced strategies such as continuous chromatography and process analytical technology. So one of the ways we can quantify the cost effectiveness of a process intensification strategy in the context of Protein A chromatography centers on the purification costs. Namely, how much does it cost to purify and recover a gram of product across a process step or campaign? So several benefits to this. It's a simpler, easier to use alternative to cost of goods. It doesn't account for hardware, maintenance, or investment returns, or even dosage costs. It enables head-to-head direct resin-to-resin comparison evaluations, as well as inter-resin evaluations looking at different scenarios, such as different bed heights. It also allows you to identify favorable parameters and optimize towards productivity and cost effectiveness. Taken together, it's an ideal strategy for process development through to MSAT teams, and it combines factors like resin price and volume, labor costs, material and buffer costs, performance characteristics such as dynamic binding capacities, the number of life cycles in context to that required per campaign, as well as flow rates. So the reason that we're sort of looking at this is because of, in the context of Protein A chromatography, is due to the high costs. So traditionally, up to 80% of bioprocessing costs are from downstream processing. And up to 70% of downstream processing costs come from the chromatography step, the Protein A chromatography step, particularly at phase 1 and 2 clinical trials. It's not as bad at pre-commercial scale, but it certainly is at earlier trials. So you can see in the chart on the left, the optimal production costs that might occur show the resin, materials, and labor cost breakdown. And those would be assuming 100% utility of the resin, whereas in reality, you typically see something like the bar chart below, which has quite a large quantity of resin being unused. And this presents an opportunity to try to reduce that, or process intensification strategies rather, provide an opportunity to try to reduce this resin cost. So advances in bead and ligand design have enabled higher dynamic binding capacities, particularly at faster residence times, to be generated. And this means that lower bed heights can be used without incurring an excessive cycle number or increased process time, which would be observed with more traditional resins that demonstrate lower binding capacities under these conditions. This point is illustrated in the two charts on this slide, which show a high dynamic binding capacity even at faster residence times. So it means that instead of operating on a 20 centimeter bed height, lower bed heights can be used, as I'll demonstrate in the coming slides. And this means that less volume can be used. So it solves that aforementioned problem in the earlier slide. And coupled with improvements in column flow distribution and bed consistency obtained from columns using axial column compression, lower bed heights are seen as a more viable option. So another quality that's important to protein A beads centers on good caustic resistance. The charts here show essentially a comparison between Presto jetted A50 and MabSelect SureLX for an IgG1 antibody. And you can see that across 150 cycles, the yield for jetted A50 remains above 90%. So that's the red dashed data points above the 90% threshold for the yield in purple, with the binding capacity only really dropping a little bit towards 130 to 140 cycles. And that's still well above the 80% threshold. And it compares very well to MabSelect SureLX in this instance. And that's using a 60-minute contact time with 0.1 molar sodium hydroxide. So bead design is also important. Jetted beads offer a much tighter particle size distribution, ranging from 35 to 95 microns versus 45 to 120 microns seen with batch emulsified beads. The uniformity coefficient is also typically under 1.3, whereas it's about 1.9 for batch emulsified beads. And this essentially means that when you're packing a column, there's the potential for a much more efficiently packed column, which eliminates voids and provides a range of benefits, which I'll talk about in the next slide. So as I said, the batch emulsified beads typically have a wider elution peak, and they often require increased buffer volume and longer cycle times compared to jetted beads. Essentially, with jetted beads, you have much more efficiently packed columns, which can result in sharper elution peaks and reduced buffer volumes. And that can also mean reductions in column cycle times as well. So in terms of process intensification with packed bed chromatography columns, there's a range of strategies that can be implemented. And this is something that we built around the jetted beads, and we sort of term smart cycling. So we can have the standard column size, we can have a reduced bed height and internal diameter of the column, reduced column volume, so particularly for non-loading steps, as well as variable flow rates. Taken together, a lot of these can lead to 3x increases in productivity, an 80% reduction in resin cost, as well as a 55% reduction in buffer volume. And I'll be talking about some of these examples going forwards. So if we take a standard process with a 60 centimeter internal diameter column and a 20 centimeter bed height, under these conditions with a feed of 7 grams per liter titer and a 2000 liter reactor, you can see that there's various strategies that we can consider. And one of these is the reduced bed height. So this chart shows a reduction or the benefits of reducing the bed height. So what I've done here is optimize the purification costs towards cost effectiveness to try to get the most cost effectiveness outcome. So the chart on the left shows productivity, cost effectiveness, time, cycle number, and buffer consumption. So the red line in the center represents the 20 centimeter bed height. Anything outside of that line represents an improvement in the performance metric. Anything inside of that line represents a reduction in that performance metric. So lowering the bed height will no doubt lower the volume of resin. This is particularly beneficial with jetted A50, as we can exploit the faster residence times, which can be obtained at lower residence times. So this doesn't really increase the buffer consumption. And more importantly, it allows a saving in processing time and an improvement in productivity and cost effectiveness. You can see for 10 centimeters, it's particularly effective at cost effectiveness and productivity. And it's worth pointing out, it doesn't have to be 10 centimeters or 15 centimeters. We've got some customers working with 12 centimeters and other customers at larger scales working with 17 centimeters. So it can be very much optimized towards your constraints and your process. And as I said, this makes it particularly appealing for studies that are looking to increase the utility from, say, 50% up to 70 or 80%, such as those at pre-commercial scale where the full capacity of the resin wouldn't typically be used. Lastly, it's worth pointing out that some customers are still reluctant to switch to lower bed heights. Whilst this was understandable with older columns, the shift or the benefits of axial compressive columns, which have been introduced, mean that you have improved flow distribution and column efficiency and consistency, meaning that the packing quality is still very, very high and very good. In terms of the performance benefits from the economic benefits, rather, you can see that in the table on the bottom right. So with the 20 centimeter column, based upon recommended retail prices of the resin, you'd be looking at about $1.28 million. For a 15 centimeter column, you might be looking at about $1 million. And for 10 centimeter columns, you could be looking at about 800,000. So there's quite a big saving which can be made here just by adjusting the bed height. So this chart looks at the reduced bed height as well as a reduced internal diameter, again optimizing towards cost effectiveness by reducing the resin volume. And the chart has the same principles as the previous one. Anything outside of the red line, everything's normalized against that, but everything outside of it represents an improvement in performance. Anything inside of it represents a reduction in performance, so something that's undesirable. So we're looking at a drop in this case of the internal diameter from 60 down to 45 centimeters, as well as a 10 centimeter bed height. And in regards to the reduced internal diameter, a bed height of 13.5 centimeters. So that's to ensure a balance between processing time and cost effectiveness without going too low. So you can see that there's obviously benefits in productivity, not as much as the 10 centimeter column, some slight benefits in buffer consumption, and a slight improvement on the 10 centimeter bed height for cost effectiveness, but there are some drawbacks as well. So it would mean that the reduction, so going inside of the red line, represents a reduction in performance in the context of processing time and cycle number. So you'd be having more cycles and you'd be having a longer processing time as that sort of strategy is implemented. So there's very much needs to be a balance between what's desirable from the metric that you optimize towards, as well as what's feasible in your facility and your lab. There's other strategies which can be used, as I talked about. So the one I'll be looking at here is reducing the number of non-loading steps, so reducing the number of column volumes, and this can provide a lot of benefits in terms of buffer consumption, as well as the costs that can be saved here by adjusting those. The reason for this represents the trend that we're sort of seeing with purification cost distribution. So the top bar chart shows the traditional cost structure that might occur for a resin, materials and labor costs chart. So you can see that it's very much focused towards resin costs. The current cost structure and the general trend we're seeing, especially with more caustic resistant resins, such as the jetted 850, you can see that the resin itself is occupying a smaller proportion of this, whereas materials and labor costs are occupying a larger proportion of it. This sort of represents the fact that protein A resins are having longer life cycles and they're having higher dynamic binding capacities. So whilst costs might be going up slightly there, the cost effectiveness, so basically the cost effectiveness of those resins over time is coming down. So it's almost deflationary. On the other hand, materials and labor costs, which are subject to inflation naturally, they're actually occupying a higher share of this cost structure. So this means there needs to be more, or there will be more of an emphasis on resin resourcefulness, so getting more performance from the resin just outside of things like dynamic binding capacity, which I'll talk about now. So When we shifted from batch emulsified to jetted beads, we noticed an increase in dynamic binding capacity because of the favorable mass transfer characteristics, but some customers also wanted to see more data regarding residual clearance, which actually improved. The chart shown here is a snapshot of that, but it shows the host cell protein levels at 1 and 6 minute residence times compared to 2 batch emulsified competitor resins. So at a 1 minute residence time, you can see that the concentration of HCP is around 70% of the competitor resins. And at a 6 minute residence time, you can see that the concentration of HCP is somewhere between 40 and 60% of the competitor resins, depending on which one is used. So we think this is attributable to the jetted beads. So there's more uniform particle size distribution and lower void volume within the packed bed, but it also could be things like the pore structure and size, as well as the surface chemistry and interactions. I'll talk about the benefits of this in a minute, but it's certainly something that we'd like to investigate with customer feeds. We are seeing anecdotal evidence that this is being confirmed, and it would be interesting to get your feedback on this. So if we go back to the original standard process, what this reduction in HCP and residual content could translate to is a reduction in the number of column volumes for washing steps, for instance. So if we take this standard process, you can see that it's in the green box, it's being reduced from 5 down to 3 column volumes for washing steps 1 and 2. So going back to these charts here, we've done it for a 20 centimeter and a 10 centimeter bed height. And you can see that there's an improvement in productivity and cost effectiveness, particularly in the 10 centimeter bed height. But more importantly, there's an improvement in the buffer consumption. So less buffer is obviously being used. In terms of the savings that this can translate to, in the table on the right, you can see that they're quite small, but this is for this particular example. I'll go into a bit more detail in a minute, but you can see that for 20 centimeter bed height under these conditions, the savings would be about $35,000 for the 20 centimeter bed height, and about, again, $35,000 for the 10 centimeter bed height. This slide shows a more in-depth overview of how reductions in buffer consumption can accumulate. So you can expect to see savings in WIFI and WIFI consumption and wastewater generation, and the economic benefits of those as well. So if we look at two different columns, so a 60 by 20 centimeter column and a 200 by 20 centimeter column, at a 7 gram per liter titer, you can see that as the number of cycles per campaign increases for both of these resins, so that would be in columns 2 and 3, the volume of WIFI and volume of wastewater being generated starts to increase as well. This trend is linear, but you can see that, at a small number of cycles is not particularly substantial, but as you start to go up to more cycles per campaign, the savings here that can be made in WIFI and wastewater can be quite large. And this can translate to financial or economic benefits. So you can see that, again, limited number of cycles. It's a fairly small saving compared to the scale of the costs associated with the campaign. But as you start to go towards 50 and 100 cycles per campaign, then the costs are more substantial. So the data in green represents the saving in purification cost relative to the standard run, where there hasn't been a reduction in column volumes. And you can see that, obviously, limited number of cycles, it doesn't have a big impact, but as the cycles increase, the savings that can be made start to contribute more and more of a share to, or start to eat into more and more of the purification costs. So what this can translate to is an equivalent saving in the cost of the resin. So if your resin is $15,000, for instance, so you can get a 5% saving here, that could equate to a reduction in that $15,000 per litre resin cost down by about $750 per litre. So there's a lot of potential benefits that can be made. And you can see this with the campaign cost distribution here. So if we take the standard 28 column volumes that I talked about a minute ago, and compare that to the reduced column volumes with 24 column volumes in this example, you can see that the campaign costs start to come down, and the buffer materials, the buffer, and in this case wastewater costs, occupy a smaller proportion. And as I said, savings here can translate to lower purification costs, which equates in itself to a reduction in resin cost as well. So taken together, there's a lot of different scenarios that can be evaluated with our tool. You can see that the total cost, which has been normalized against the 20 centimeter bed height for the standard column for various scenarios, has been displayed. So that's in column 1. The red dashed line represents that, and everything below that represents an improvement. So the bars look at resin materials and labor costs, with the orange dot being the time, or the process time. Sorry, the batch time. So you can see that everything represents an improvement against the original benchmark. And in particular, a reduction in bed height can translate to a lot of cost savings here. Particularly for 10 centimeters in this example. So looking at 3 and 6, columns 3 and 6 rather, you can see that there's quite a large saving, and the process time, or the batch time, is coming down as well. And looking at the reduced internal diameter in columns 8 and 10, there's some slightly larger cost savings which could be made compared to the 10 centimeter bed height, but it's worth bearing in mind that the time is increased. So it needs to be, any option that you select needs to be a balance between, or a trade-off between, what is practically feasible and what you'd like to aim for in the from a more theoretical perspective. So to summarize, I've talked about process intensification strategies that can improve protein A capture step performance and cost effectiveness. I've talked about purification costs and how they're a useful way to quantify cost effectiveness. And I've talked about jetted AAT beads, which are uniquely positioned to support these types of process intensification strategies, as well as jetted AAT beads, which could facilitate lower bed heights and could reduce WIFI and wastewater usage, as well as make savings in terms of costs there as well. So that concludes my talk. Thank you very much for listening, and I'll be happy to take any questions.